Have you ever wondered how a device can achieve such precise control from what seems like an inherently unstable component? In the world of electrical engineering, particularly with operational amplifiers, we often encounter ideal characteristics that, while not perfectly real, are incredibly powerful for understanding and design. Today, we will explore one of the most fundamental of these concepts: infinite open-loop gain. For an ideal operational amplifier, or op-amp, infinite open-loop gain means that the op-amp will theoretically produce an output voltage that drives the voltage difference between its two input terminals to exactly zero. It signifies an immeasurably large amplification factor when no feedback is applied, pushing the output to its maximum possible value with even the slightest input difference. Now let us delve into the why. Open-loop gain refers to the raw amplification capability of the op-amp without any external feedback network connected between its output and input. The assumption of infinite open-loop gain simplifies complex analysis because it implies that, if the op-amp is operating in its linear region, any non-zero differential input voltage, no matter how small, would theoretically cause the output to immediately swing to one of its power supply rails, either maximum positive or maximum negative. This extreme sensitivity is crucial. When negative feedback is applied, this infinite gain forces the voltage difference between the inverting and non-inverting input terminals to become zero, a condition often referred to as a virtual short or virtual ground. This occurs because the op-amp, with its immense internal gain, tries to eliminate any input voltage difference, and the negative feedback mechanism provides the path for it to do so. This powerful simplification allows us to analyze op-amp circuits with surprising ease. First, because of the virtual short, we can assume that the voltage at the non-inverting input is essentially equal to the voltage at the inverting input when negative feedback is present and the op-amp is in its linear operating region. Second, we can assume that no current flows into the input terminals of the op-amp. These two fundamental assumptions, derived from the concept of infinite open-loop gain and infinite input impedance, enable us to apply basic circuit laws like Kirchhoff's current law and voltage divider rules directly to the external components, rather than getting bogged down in the complex internal workings of the op-amp itself. The true value proposition of infinite open-loop gain lies in its role in making operational amplifiers incredibly versatile and predictable in linear applications. This theoretical concept explains why, when negative feedback is used, the overall gain of an op-amp circuit becomes almost entirely dependent on the external feedback components, rather than the op-amp's internal characteristics. This means that a standard op-amp can be configured to perform a vast array of precise operations, from amplification and filtering to integration and differentiation, with its behavior dictated by stable, passive components like resistors and capacitors. So, while no real-world op-amp possesses truly infinite open-loop gain, understanding this ideal characteristic is paramount. It is the cornerstone assumption that unlocks our ability to quickly and accurately analyze and design a multitude of practical op-amp circuits. It allows us to focus on the desired circuit function and external component values, making what could be a very complex problem elegantly solvable, and transforming a high-gain device into a precisely controlled building block for sophisticated analog systems.